All right, my friends, let's get going here. So for Form A, for problem 1, the claim that was correct was claim 1. And so, and you get 2 points for demonstrating in your proof that you knew that it was claim 1 that was the correct claim. And then if you chose the wrong claim, there will be places within your proof where you can still earn some partial credit, but there will be some places where you wouldn't be able to earn it as well. So let's go through that. So getting started with the basis step, that would basically be showing that your first partial sum on claim 1 on the term-by-term side would just be 7. And then showing that you could generate that value by using this formula as well when n is 1. And then it's kind of simplifying it in your head for the most part, and then, yep, it works. There you go. So 1 point for the basis step. Okay, now for the inductive step. Okay, the inductive step has 2 pieces. There's the assumption piece, and then there's the moving from your assumption to showing the claim is also true for n equals k plus 1. So for the assumption, we would say, we assume that, okay, and then you could write the words, there exists, or you could use the math symbol for it. You'd have to use the correct symbol though. There exists some value. We'll call it k, and it needs to be from the natural number set. Again, you can say such that, or you could use this symbol for such that our claim holds true for n equal to k. Okay, 1 point for saying that line there. Okay, now let's kind of be clear as to what our claim is. So our claim is that the sum of the first k terms, which is defined as this, our claim is that you could use this formula to get the sum instead of doing the term by term. There we go. Okay, 1 point for that line. Okay, next line. Now, so that's the end of the assumption piece. Now we just need to move forward to kind of creating that loop that if it works for k, n equal to k, then it would also work equal to k plus 1. So now, all we must show is that our claim also holds true for n equal to k plus 1. Okay, and 1 point for that line. Okay, now let's get started. So for this piece, you're going to start by showing the term-by-term expansion of what the first k plus 1 terms would look like. Well, the first k plus 1 terms would have everything up to the kth term, and then it would, oops, I have a mistake here, I apologize. I should say 7k, sorry guys. All the way up to the kth term, which would be 7 times k, and then it would have the k plus 1 term as well. Okay, this is not the part we're arguing. We're basically, our goal is to show that I can get this term by term expression if I use my assumption. I can get it to simplify and end up being exactly this formula, just where n is k plus 1. So this is my goal. And you don't want to write this here. I notice some people write it here. If you write it here, you'll need to take off a point. It needs to be clearly as part of your scratch work, something that the reader would not look at. It's just for you off to the side. So if I can make this look like that, then I've finished my inductive proof, my inductive step. So the trick is to lean on your assumption. So your assumption is that these terms could be swapped out for 7k times k plus 1 over 2. But then you'd have to bring down that k plus 1 term that would be extra. And then you'll need here, you'll need to say by our assumption. Okay, so some points. One step for just the term-by-term expansion of S sub k plus 1. 2 points for swapping in this formula for the first k terms. That's an important step right there. 1 point for also bringing down the k plus 1 term. And 1 point for saying by our assumption. So that line is a pretty important piece in your proof. Okay, now it's just a matter of using factoring techniques to show that you could factor it down to equal this. So there are different ways that this part could look, but here's kind of a standard where like you just get common denominator at first. And then you could add fractions together and factor out the common factor on the top. The common factor, the greatest common factor would be 7 and k plus 1. And then you could multiply it into k plus 2. And then the only difference between this and what it is, what my goal is you kind of unsimplify the k plus 2 to look like k plus 1 plus 1. There we go. Okay, now we just need our summary, but let's give you some credit along the way. So 1 point for passing through this factored version in your work, and then 1 point for then unsimplifying it to be a very literal interpretation of this formula just with the n's replaced with k plus 1s. Okay. Okay. So the last thing we need to do is just a summary. So you could write the word therefore, or you could use this little math symbol here that means therefore. So therefore, the sum of the first n terms defined as looked at the wrong thing. 7 plus 14 plus 21 plus all the way down to 7n is indeed equal to 7n times n plus 1 all over 2. For all n from the set of the natural numbers by mathematical induction. Period, and end of proof, QED, or the little box. Okay, so last 2 points are for this entire thing, symbol by symbol. You got to have it all. So that is worth 1 point. And then saying by mathematical induction is your last point. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. If you got 15 points, circle the 15. If you got partial credit, you could always just write a fraction over 15 here.